This is Derek, and this is section 8.2 or 12.2 in the COREC, and this is going to be the sums of the terms of sequences. So if you remember in the last section, we had a list of numbers, so now we're going to take that list and then add them all together. And so that's actually called a series when we sum a sequence, but that's essentially what this is. This section, this notation, looks like it's going to be awful, and then it turns out it's a couple of formulas it is not too bad at all. So let's get this notation out of the way. Summation notation. The sum of the first n terms of a series can be expressed by the summation notation below. So we have this kind of funky looking Greek letter. This is sigma, capital S, and that stands for sum, that we're going to add these terms. So that's just indicating that that there's addition that's going to happen. The index, so that's this. The index I starts at 1. In this case, it can be other letters as well, and we'll see that in examples. In this course, we're going to have this start at 1, but there's some things you can do in later courses where you shift this index around. This is going to be the lower limit, so this is saying we're going to start on the first term in this case, and then n is going to be the upper limit of the summation, so that's going to tell us how many terms we're going to sum through. So like looking at this example right here, we're starting with our first term, so that's our lower limit of our summation, and we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9 would end up being our upper limit. And then this a sub I, this is telling us what are we summing? What are the terms going to look like? So this is the expression that would be evaluated, like we saw in the last section, and then that's what's going to produce the terms that we're then going to add from here to here. Let me show you with some examples, and it is not as horrible as all that makes it seem. So first off, they're going to just try to get you to fill in the summation notation. So express the arithmetic sum using this notation. Use n for your variable starting at n equals 1. Okay. So they're telling us in this case, so here I have it as I for the index, and already they're changing it up to an n, and we'll see that all over the place. We're going to sum from the first term, and then like I said earlier, we counted up, there's going to be 9 terms. And then what I have to do here is figure out how to say what this is, where this is the first term, this is the second term, third term, etc. So here the first term is 7, the second term is 14. When I put in a 3, I'm going to get 21. When I put in a 4, I'm going to get 28. So you can kind of see there, it's starting on 7, and then it's increasing by 7s. So it's just 7 times 1 makes 7, 7 times 2 makes 14, 7 times 3 makes 21, and so forth. So 7n is what you would be evaluating from 1 to 9. Put in 1, you get that, 2, you get that, you get each of these numbers, and then this sum means we're adding them up like that. So this and this right here, those mean the exact same thing. This is just the shorthand way of writing that. The next one, express the geometric sum using summation notation. Use the variable n, start with n equals 1. Okay, so they told us it's geometric, which is awesome because we totally know what form this is going to take. Remember, that is the r, the a sub 1. Actually, let me just pull it up here really quick. I have it right here. So what I'm plugging into is this formula from the last section where we have our first term and our ratio. So our first term is 1, and our ratio, 3 over 1 would be 3, 9 over 3 would be 3, so our common ratio is 3. So I have like invisible 1 times 3 to the n minus 1, because that is our geometric sequence nth term formula. So that's what went here, and then I just counted, there's 7 terms, so I'm going to plug into this formula that will make those 7 terms, and this is saying I'm going to add them. And then after we get past that, now it's using some formulas, and much like that last chapter or section, we have formulas for arithmetic, we have formula for geometric. So we'll start with the arithmetic, the same as we did last time. There's 2 versions of the formula. They do the same thing, but it just is dependent on kind of what you're given. So the sum through the nth term. So now if this said s sub 10, I would be summing the first 10 terms, and that's what this formula would do. So n is still our term, our first term, a sub 1, and d. So all the same players as last time. For this version of the formula, if I know the difference, cool, that's great. I need n and a sub 1 either way, but in this one I don't have to know the difference, I just have to know the nth term. So if I know the nth term, this one's better. If I know the difference, then this one would be better. So it just sort of depends what pieces we're given. So let me show some examples. This first one, we got use the formula for the sum of the first n terms of each arithmetic sequence. So we're given this, told it's arithmetic. Our first term is 27. Our difference is easy enough to find. It looks like we're counting up by 5s, so a difference of 5. We know our nth term, in this case, is 67. We don't know n though, right? And so in either one of these formulas, I do need to know n, so I'm going to have to do something about that. Because to find the sum, I need the n. So I do have my last term here, and I do have my first term, but like I said, in either way, I don't have n. So what I do is I go back to this formula from the last section to find my term. So we have a sub n equals a sub 1 plus d n minus 1 again, and I know my 67th term, or 67 is the term that corresponds to the n I'm interested in, because this is that last term. So I'm going to do 67, my first term is 27, d was 5, and now I can solve for that n and the n minus 1. So I brought the 27 over, and I divided out the 5, added over, and then learned that n is 9. Once I got that, I could plug it into either formula, but this one's easier, so I picked the easy one. There's my first term, 67, that was my last term, or my 9th term, and then just toss that all into a calculator. So very, very formula driven. If you're trying to find the sum of the first n terms of an arithmetic sequence, this is it. It's one of these two things, and basically you just have to find all the pieces in one or the other versions, and that's how you're going to do it. For finding the sum of the terms of a geometric sequence, we have a couple of things that can happen. So a geometric sequence, if we go to an arithmetic sequence, let me back up. If we add terms to infinity in that, it's going to go to infinity. With a geometric sequence, that is not necessarily the case. And so we're going to have to see, we're going to have two formulas. We're going to have one where, whoops, wrong one, pop this one over, where there's n terms, so where it's a finite sum, and then we're going to have one where it's an infinite number of terms. So if we keep adding these things forever, it goes to infinity. If you are wondering how can you add things forever and they go to infinity, a really common example of that is if you think of adding 1/2 plus 1/4 plus 1/8, that will actually go to 1. And the reason is, if you think of this little box here I have is area 1. If I cut that in half and I added a half, and I cut the remaining bit in half, and then I'd be adding a quarter. If I cut that remaining bit in half, I would be adding an eighth. And you can see I could just keep cutting what's left in half, and I'm going to get closer and closer to 1, but I'm never going to get there. And so that's what's called converging, so that sum of that infinite geometric sequence would be converging at 1. So if you do 1/2 plus 1/4 plus 1/8 plus 1/16, you'll get closer and closer to 1, but never get there. So there's an example of something that can do that. Versus if I had a geometric sequence that was, 2 to the n essentially, I get 2, 4, 8, 16, that's going to add to infinity. So there's this issue that to have an infinite geometric sequence, the ratio of the terms has to be less than 1. And in that case, then we have the situation. If r is equal to or greater than 1, then that means there isn't a sum, it goes to infinity. And I'll show you that case as well. So for the geometric down here, use the formula for the sum of the first n terms of a geometric sequence to find the indicated sum. Do not round your answer. Okay, so it looks like we got our first term is 1. Our ratio 3 over 9 would be 1/3, or 1 over 3, also 1/3. And we got 1, 2, 3, 4, 5 terms. And then looking at this formula, that is absolutely everything I need. And then the worst part is just kind of grinding out the fractions in this. So let me show you how I did the arithmetic here. So there's our ratio 1/3, that's to the 5th. So that's just everything plugged in. There's our first term. So here I did 1/3 to the 5th would be 1 over 243. And again, I'm just going 3 to the 5th, 243. If you put that in the calculator, it'll give you the decimal. So just realize it's 1 over that value. And it's asking for don't round your answer, so it wants this in exact form. So that got me here. And then 1 minus 1/3 would leave me 2/3. And then 1 minus 1 243rd would leave me 242 243rds, if that makes sense, because this would be 243 over 243. And then this is a complex fraction, so I could do fraction divided by fraction. What I did was I just brought this up and flipped it over. So if you think of that 2/3 coming up, and remember we multiply by the reciprocal, so that's how I got that 3/2. So instead of writing it like this, I'm writing it side by side with the flip to do the multiplication. And then I did a lot of canceling. So I think 2 went into that 242 121 times, and then 9 must have gone in there. Oh, there's actually 27 up top, so I think I did 27 into 243 would leave 9. So after a lot of reducing, there's my sum through the first 5 terms. This next one, use the formula for the sum of the first n terms of a geometric sequence, find the sum. So we're looking for the sum through the 6th term of that. So in this case, we got our first term is 7, our ratio 21 over 7 would be 3, and s sub 6, so that sub 6 down there is telling us n is 6. After that, it's very much just grinding out the math again with the calculator. So the sum formulas really are not terrible. Number 6 here, use the formula for the sum of the first n terms of the geometric sequence, find the get sum again. So we have, we're going to sum from 1 through 8, so that tells me n is 8, and then this is geometric, so my first term would have been a 1 right there because of the invisible 1, and my ratio is 3 given in the formula. And then from here, I'm just coming right back to that summing. It's a geometric sequence, and I'm summing some number of terms, not infinite terms. So that makes it this formula. And I'm just plugging in the things I know. So the sum through the 8th term, there's our first term is 1, our ratio, and then again, more grinding out math in a calculator. And then here we are at the infinite geometric. And so this is what I was talking about earlier, that if the ratio is less than 1, then it has a finite sum. If it's greater than or equal to, it will not. For this first example, this 1/4 right here is some sort of typo, so I need to go clean that back up out of the notes, so just ignore that. I think that probably should have been like a ... or something. So the question is, determine whether the infinite series has a sum. If so, find the sum. If not, state the reason. So first off, it has to be geometric, so let's see if it's geometric. If I do 4.8 over 8, I get 0.6. If I do 2.88 over 4.8, I get 0.6 again. So it has a common ratio, as long as we ignore that 1/4 there, that's my typo. So it is geometric, and the ratio was less than 1, right? It came out to 0.6, and it's less than 1, that meets our criteria, so this is going to have a sum. And then since it has a sum, now we can use this formula. Our first term was 8 minus over 1 minus the ratio. And then just tossing that into a calculator, that means if you add this forever, these numbers will approach 20 without ever actually getting there. Determine, same thing, it has a sum. And then this one, let's see, so this is, they used x this time. It is geometric, right, because it's in the form of an exponential, but the common ratio on that's going to be 8, because the base of the exponential is 8. So it's geometric, but r is greater than 1, so the sum does not exist. Number 9, so find the sum of the infinite geometric series again. And so we're given our first term is 4. Our ratio is 1/3, and there I am just plugging into the formula, and that's going to give us our infinite sum there. I should not have that n, that should just be an s, another typo on my part, sorry. And this equation is the exact same thing. This one just has a fraction, that one has a decimal, but same exact math. And that concludes 8.2 or 12.2, and I think that should be our last section for the course.